reactions of copper. So we are going to start with 0.4 grams of copper. When we add nitric acid, we will change to copper nitrate. To the copper nitrate, we are going to add sodium hydroxide. Reaction of sodium hydroxide with copper nitrate is going to give us copper hydroxide. Copper hydroxide, we are going to heat it up. We heat it up, it's going to change to copper oxide. Copper oxide, then we add H2SO4. With H2SO4 is going to change to copper sulfate. We are going to add zinc or magnesium. We're adding magnesium, Mg, either one will work now. Mg, you should recover 0.4 grams of copper. What is the purpose of the experiment today? By cycling copper through this different set of reactions, we are going to learn about chemical reactions, what type of chemical reactions, and in your data sheet, the question that each part of the experiment is asking to copy the chemical reaction, but each chemical reaction is explained in the introduction part of the experiment. I'm sure you have read it already. So we are going to learn about different types of the chemical reaction. If you have like oxidation reduction, or if you have like decomposition type reaction, or single displacement reaction, and we are going to also learn different lab techniques. The lab techniques that we are going to learn, one of the lab techniques is like decanting. Decanting, if you have a mixture of solid and liquid, you have two ways to separate them. One is decanting, the other one is filtration. When you are decanting, you are pouring off the liquid, the top liquid, without getting any of the solid into the other container. So that is called decanting. When you are decanting, when I do the experiment, I'm going to actually show you how to do the decanting part. But just as a demo, when you have a mixture of the liquid and the solid in one beaker and try to decant, you are going to use a stirring rod. You hold the stirring rod with like 45-degree angle, and then slowly you pour only the liquid portion, and you are careful that no solid is going to be transferred. So that's one of the technique, and is decanting. You're not going to get all the solvent or the solution out, but you will get most of the solution out. You would separate most of the solution. The other technique that you are going to learn is filtration, gravity filtration. And for gravity filtration, the setup looks like this. For the setup, you're going to have a glass funnel, proper size iron ring, and a receiving container to get the decantant down the filtrate. So you get the filtrate, you receive the filtrate through the filter paper. To prepare the filter paper, you're going to cut the, just fold it, not cut. Fold the filter paper in half. And then one more time, you would fold it in half. You open it in a way that one side of the filter paper is in, one part is on one side and 3 parts is in the other side. Basically, you are making a paper funnel. And when you make the paper funnel, you place it inside the glass funnel. Sometimes it doesn't stay still. And if it doesn't stay still, all you have to do is add a few drops of water. So if you add a few drops of water to the filter paper, it's going to stay still. It would stay down and then is not moving up. So it's a good practice to add a few drops of filter paper. Then you are going to pour the mixture of the liquid and solid that you have in a step of the experiment. You would pour it into the filter paper. The solid would stay on the filter paper, and the liquid would be passing through the filter paper, and you will collect your filtrate in a receiving container. Yes, exactly, like a coffee filter. Exactly, yes. The setting up here is slightly, it kind of makes sense, and I'm glad, just like coffee filters, yes. So we are going to learn about how to heat up the reaction, like heating up reaction mixture. We are going to learn about decanting. We learn about the gravity filtration. We are going to study the law for conservation of the mass. Ideally, if you start with 0.4 of copper, after you cycle the copper through all these reactions, you are going to, after you cycle the copper through all of these reactions, at the end, ideally, you're expected to get, you get 0.4 gram of the copper. Now, are we going to get 0.4 gram of copper? Maybe not. Why not? If at the end of the experiment, if the filter paper that we are using to dry up the copper, for those of you who read the experiment entirely, if it is wet, or if your copper is still wet, is going to weigh more than just copper. So is the copper plus the solvent. The magnesium that you are adding, if it doesn't react completely, and you don't add extra acid, or you don't wait long enough for magnesium to react, if there is leftover magnesium is going to add up to the mass of copper. So you could get more than enough copper, so the mass could be higher than 0.4. If you don't wash your copper properly, some of the copper sulfate salt or other salt like sodium nitrate salt, it can stay with the copper, and when it dries up, it's like if you have salt water and you evaporate the water, you end up with the powder salt. So it's in it's in solution. It's not visible, but when it dries up the solvent, when you dry up the solvent, you will see the powder forming. That could add up also to the mass of the copper, so you get more than 100% recovery. So those are some ways that you could get more than 100% recovery. Now, how could you get less than 100% recovery? Sometimes I've seen students getting like 30%, 40% recovery. What could cause less than 40% recovery? Let's say the step we were decanting, if we decant some of the copper out. When we are filtering, we lose some of the copper into the copper compound into the filtrate that we are collecting, and then we discard it later. If we don't add enough magnesium, if the reactions are not complete, if we don't add enough reagent in general to make the reaction complete, then you are going to lose some of the copper. Like when we are adding sodium hydroxide, if we don't add enough sodium hydroxide, the reaction is not going to be complete, and some of the copper would stay in the solution form and doesn't change to the to solid. Like this compound is solid. Use S for solid. That's solid. This compound is an aqueous solution. AQ, that stands for compound that is soluble in water. And then copper nitrate is an AQ. Also, it means it's soluble in water. So if you don't add enough sodium hydroxide to this solution, you're not going to get enough of the solid for the next step. Okay, I'm going to start the experiment, and I will explain as we are performing the experiment. So at the first step of the experiment, what should we do? You can take a screenshot of that board, and that would be one of the screenshots. I'm afraid that if it's up, then it would be blurry. So is it better now? Okay. Okay. 'Cause, 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 'cause Okay. So you would use you are going to measure 0.4 grams of 0.4 grams of copper. To measure 0.4 grams of copper, we are going to see. Okay. We are going to place the weighing paper on the balance pen. Press there to get it 0. Add enough copper to make it 0.4. Okay. So we have 0.407. 0.407. That was the mass of the copper that I started with. So you can record that mass. 0.407 was the mass of the copper that we start with. Next step. What is the next step? Can you tell me what's the next step? No, you're looking at the data sheet. I want to make sure that you're not looking at the data sheet. You're looking, when you are in the lab, you have the procedure. When you look at the procedure is going to tell you when to get the mass of the filter paper, when to get the chemicals, and what are each step. So I want you to tell me, using the procedure, what is the next step after measuring 0.4 grams of copper. Place the copper in 250 ml beaker. Yes, very good. And next, I am using my gloves. That means that we are going to work with strong acids. We're going to add HNO3. HNO3 is highly corrosive. It's very strong acid. And inside the fume hood, we are going to add 5 milliliters of the nitric acid. You see the fumes? I don't know if you could see or not, but these fumes are coming out. It's very strong acid. Copper is not a very reactive metal, but nitric acid is very strong. So when I add the copper to the nitric acid, you will see now that it's going to generate fume. Okay. That fume, I don't know if you see or not, it's up here. You see it now? It's very toxic. And you should be happy that you're not here to inhale this fume, because the fume hood is not on. I'm giving some time for the fume to go away, and then I come back to add the water. So also copper needs to dissolve. Okay. The brown gas, which was toxic, is now gone, and it's safe for me to work with this solution. What I want you to do, I want you to write your observation. Write your observation after adding nitric acid and water, because I had to add the water first before I can take it out. I add the 100 mils of water before I can take it out. So write your observation and tell me what is the next step. What do you want me to add to this? Yes, deionized water. I added the 100 milliliter of deionized water. What is the next step based on the procedure? And what do I need to add? And how much? Okay, what should I write now? What? Okay, 20 milliliters of, is not the 0.6 actually, it's a 6 molar. 6 molar, 20 milliliters. And as I'm adding, I want you to record your observation when I'm adding to this. The change in color, also change in texture of the solution.
So just put some of those values in the image tomorrow.
Okay. Thank you. Well, I can come at 12:30. Thank you. Record your observation, please. And tell me what is the next step. Next step, heat. Okay. We're going to place on hot plate to heat up the sample. You're going to heat up the sample. And the next step is going to be, yes, it's a darker blue color. And also the texture has changed because it's not clear liquid anymore. You have solid compound, and that solid is the copper hydroxide that has formed. I would do occasional stirring, not constant, but occasional stirring. I'm going to have to heat it up until is dark, black color. The shade of the blue needs to disappear and it changes black color. That is the time that I know copper hydroxide has changed to copper oxide. So CuOH2, that's what I have now. It should change to CuO. Is another step of the oxidation. And removing water. Is removing water, so you could classify as decomposition reaction because CuOH is changing to CuO. Decomposition also. Your question, if you could please type question on the chat, so I'm watching it now. If I missed your question, please say it again. Yes, it's like a, yes, it looks like a jello. Yes, yes, it is. The liquid is not a, okay, I see what you're saying. So it's not the whole thing changing to solid. A solid compound forms that is not soluble in liquid, and if it's not soluble, so it would stay as particles in the liquid, so you have like a mixture of solid and liquid now. So with the mixture of solid and liquid that you have, that it looks like a blue color, like a slushy, no? Or like the gel that you said, but it's like particles of the solid that is moving around in the liquid. So if we leave it alone, it's going to settle down. And then you could see the solid layer at the bottom and the liquid on top. So the solid has formed, but not the whole thing changes to solid. Basically, copper nitrate, when it's in the solution form, you don't see anything because it's clear blue color solution, is transparent. But when copper changes to copper hydroxide, because it's insoluble, it will make the solution cloudy. And the cloudy solution that is forming, that's indication that a solid compound has formed. And that solid compound that is forming here, we know is a copper hydroxide. You're welcome. So I don't know how clear you could see. Is the color is changing now? Is darker. Some black color is mixed with it. And then we will see when it's all black, when the shade of blue color is gone, then I stop heating. I put the computer on mute earlier when the action was taking place because the fume hood was not working. I had to call for someone to come check on the fume hood. That's why it was on mute. You couldn't hear me. Okay. While this one is heating up, we can get ready for the next step. What do we need to do for next step? Allow to cool. Okay. So when it's all black, we take it out. It's not just cooling. Also, it needs to settle down. When it settles down, then we take the clear liquid. We transfer the clear liquid. Basically, we decant the liquid into another beaker. You gave me all the steps. That's good. Is it 25 milliliters of H2SO4? Okay. I'm going to add some water. When it's all black, I'm going to add some water to it. It cools off. It's easier to handle. At the same time, it helps me wash the solution and remove any excess of sodium hydroxide that is in there. Is it all black? Should I stop the heat at this point? It looks like it, right? Yes, okay. You agree? Okay. Yes, you're right. It's all black. I'm going to stop the heat. And we have to allow to cool, not just cool. Also, it needs to settle down. And when it does settle down, we can take the clear liquid, transfer to another beaker. So I'm just going to wait for that part. While this one is settling down, I'm going to measure the 25 milliliter of 3 molar sulfuric acid you told me. I will bring it here to the station while this is settling down so I could use the time efficiently. I have the 25 milliliters of sulfuric acid ready. The solution is getting clear. The top of the solution is getting clear. I'm going to wait for it to settle more. What are we adding after sulfuric acid? Do you have it up there or not yet? After the sulfuric acid, maybe I can magnesium. Okay, maybe I can measure the magnesium while we are waiting for this. That way we're not rushing. And I don't like to rush for experiment anyway, but I like to use the time more efficiently because there's a step of this experiment that it takes longer, especially like when you add the magnesium, it takes much longer compared to the other steps of the reaction. So I can save some time for that. And also, while you're waiting for one part of the experiment, you prepare your equipment and the chemical for the following steps. Okay, let's take the camera to the other way, turn it around, and measure. How much of magnesium is that? Is it 2 grams or less? of the magnesium. How much? 1 gram magnesium? Okay. So we are going to measure about 1 gram, or approximately 1 gram of magnesium. Okay, that's 1 gram of magnesium measured. Okay. You see the clear liquid here? Is it visible? I don't want to disturb it. I don't want to take it out. So maybe if I put this white background, you could see the clear liquid, right? Okay. Now I'm going to decant the top liquid into another beaker. So I have to be very careful not to disturb it, because if I disturb it, then I have to wait until it settles down again. So while I'm doing the decanting part, you can actually take a screenshot to have it for your record. So I'm holding the stirring rod with the 45-degree angle, and I'm pouring the liquid only, being careful that no solid would go in. It's impossible to avoid like any particles, but we try to minimize it as much as possible. Okay. When the clear liquid is decanted, now going to add sulfuric acid. And what is going to happen when I add the sulfuric acid? Do you remember? After I add the sulfuric acid, it's going to actually change color. It's going to dissolve in sulfuric acid, and it's going to change from black color back to a blue color, but this blue color has a different shade now compared to the first blue color you had. Almost similar, but it's not exact same thing. The first blue color you had was for the nitric acid added, and it was like copper nitrate. This is for the sulfuric acid, and the blue color is coming from copper sulfate. Okay, with the copper sulfate, now we add the magnesium. The only problem with the magnesium is that it's going to give up hydrogen gas. So we have to make sure there is no open flame. And I'm not going to stay next to the setup and inhale those hydrogen gas. So I try to avoid inhaling of the hydrogen gas. The reaction is taking place now. I had the gray color magnesium to blue color solution. So what is happening now, magnesium is replacing copper from copper sulfate. So magnesium goes into the solution and it forms magnesium sulfate. Copper comes out of the solution. How do we know we are getting copper? Because copper has red color, magnesium has a gray color. And we get the red color or cupric color particles, and those are the recovered magnesium. So we get the magnesium recovered. Now the bright blue was after adding the sulfuric acid. When you add the magnesium, ideally the blue color should go away. It doesn't go away 100%, but it gets very light. It will get very light because the blue color is coming from copper in the solution. Trying to stay away. Okay. You see the blue color is kind of there's no problem. Why do I have to reload it?
Professor, I'm not sure if you can hear me, but you were kicked off. I'm not sure if you were aware of that.
I know, I got it, but it's okay now, right?
I can't see you at least.
You could use the chat now. Very good. Please use the chat so I could see the problem. Perfect. Okay, perfect. So now we want to make sure that you can see what is happening here. You see the light, the blue color, it kind of disappeared, and now it's getting colorless, it's getting close to a colorless solution. And I'm going to hold it close so you could see the red color particles that is coming back to out of the solution. And those red color solutions, those are, red color particles, those are the particles of copper that is coming out of the solution. This type of reaction is called single displacement reaction or replacement reaction. So what is happening, magnesium is going into solution, copper is coming out of the solution, and you see those red particles. The extra sulfuric acid, the 3 milliliter that was used in the procedure, that extra sulfuric acid is to remove any leftover of magnesium. I just look at this and there is no really leftover of magnesium, so I don't have to add the extra sulfuric acid to this mixture. I added some water to see if I can see any magnesium left. I don't see any magnesium left. So because no magnesium is left, I can wait for bubbles to stop, or I can decant and move on to the next step of the experiment. But what we want to make sure is that all the magnesium has been reacted. This step of the experiment, just like the decanting part, it takes longer. Just have to be patient, wait, watch to make sure the reaction is complete before we move to the next step. Is the next step decanting or filtration? After adding the sulfuric acid, because I'm not adding sulfuric acid, there is no leftover of magnesium. Is it decanting or filtration? Filtration? And in this step, you need the mass of filter paper, right? Okay, so we need to set up the filter, the gravity filtration. First, we measure the mass of filter paper because we need the mass of the filter paper. I'm going to measure mass of filter paper and I'll let you know so you could record it. First we tear and then place the filter paper. Mass of filter paper is 0.946. Okay. If you want to take a screenshot, you can. 0.946. Good. .946. If you cannot see, just write that number then, please. Yes, 0.946. And this, I'm not using the other filter paper because the other filter paper, I didn't measure the mass, as I showed you for setting up. So I'm going to set up the gravity filtration. I'm going to set up the gravity filtration with the paper that is already pre-weighed. Place in the funnel Add few drops of water. And filter this. Okay. To filter it, because I want the solid to be in the filter paper, I'm mixing it to make sure that all the solid is going to transfer. And if there is anything left over in the beaker, what we can do, we could add some distilled water and wash it with the distilled water and transfer into filter paper. Probably could see the red color more obvious and better now for formation of the copper. If you could please look at the procedure, or if you remember from reading the procedure, you give me the next steps while I'm doing the filtration. So it's just simply transferring the solid with using some extra water, which serves two purposes. One, transfers all the copper in. Second, it washes the copper. So basically, I'm done with washing with water. Just give me the next steps after washing with water, please. Okay. Next step after washing with water, we're going to wash it with ethanol and then acetone. Okay, perfect. Going to measure 10 milliliters of ethanol. And measuring 10 milliliters of acetone. Okay. That's 10 milliliters of the acetone, and I have 10 milliliters of ethanol also, which I measured. Okay, that's the 10 milliliters of ethanol. I have the 10 milliliters of ethanol, and when we are washing with the ethanol, basically we want to make sure that all the water is replaced with ethanol. So we kind of pour the ethanol not just on the copper. We are going to pour it over the filter paper. So to make sure that the filter paper also is washed with ethanol. I need to get another heating lamp. Okay, after washing with ethanol, now washing with the acetone. Can I please get another heating lamp? Heating lamp, please. Another heating lamp. Okay. And in order to place it under the heating lamp, there's something wrong with this. I cannot adjust the height or the angle, so I'm looking for a new heating lamp. You should get it. When we take the filter paper, we open it. You have to open it, and we are going to place it on different layers of paper towel. So the liquid or the solvent is absorbed by filter paper, and the heating lamp from the top is going to Okay, what are the precautions using the heating lamp? When you turn on the heating lamp, this gets really hot, so you should never touch the surface of the lamp. That's so you want to make sure that you don't touch it. You don't want to leave the paper here unattended because it can catch on fire. So first, we are going to get some paper towels. And we take the filter paper from the funnel, open it, and start heating. When the filter paper is completely dry, then you know the copper pieces particles are moving around, then we can make sure that the copper is dry. And then we can measure the mass for the copper. See? It absorbs the water from the water, and then the heat from the top, it will dry up the copper. We don't want to measure the mass of the copper while it's wet, because then we think that we were alchemists. We started with 0.4 and we end up with more than what we started with, which is impossible, right? Because we are studying the law for conservation of mass. One rule in the lab, when you are using gloves working with acids, when your gloves changes color, if it turns like yellow color, you need to change your gloves. That means that you had you have some chemicals on it or acid on your gloves. You don't want to touch your skin with contaminated gloves. There are only two sizes of gloves here in the lab right now. I should get another box, different size, because it's either small or extra large. So takes longer. Okay, I see some questions. The practical lab is not a practical lab, it's like a question, really. It's the question and answer, very similar questions you have on the pre-lab or data sheet. So similar questions you have in the pre-lab, similar questions you have in data sheet. And then what else? What you learn about the safety and some of the techniques that you learn in the lab. So basically general understanding. And if you attend the lab and you ask your questions, you answer questions, you participate, you should be fine with the okay. You should be fine with the exam. Now the next question is, does it have to be exactly 10 milliliter? 10 milliliter is like sufficient enough to wash the paper, filter paper, and there's really for washing, because it doesn't dissolve the copper. If you were washing with something that there was a chance to dissolve the copper, then no, you should not use too much. But if there is no chance for dissolving copper, it's just washing the other impurities, then it's okay to use more. So it's not a strict amount. The color of the gas, it was a nitrogen dioxide, NO2 gas. And NO2 gas was really, is a toxic gas. You don't want to inhale it. Okay. The copper is kind of moving around, but the paper still is sort of wet. So I'm going to wait another minute to make sure that is completely dry. Just one more. Yeah, the paper looks crisp, so. When the copper is dry, the paper looks dry. And if I bring it here, you can see like, I don't know if it's here or not, but it is dry. You can place the paper, filter paper with the copper on balance on the scale and measure the mass. Let me know if you can see the number. If not, I have to read the number to you. What number do you have there? Do you see it? 1.285. Okay, 1.285. 8485, perfect. So did you take a screenshot? Yes? You can take a screenshot. Because you can see the number. Take a screenshot and that would be a proof of the experiment. Okay. Lower. I try. Okay. Good. Top half. Do you see it now? Okay. Take a screenshot. .305 is showing that number now, so you can record that. The material, the substance now is more room temperature, so is a valid number. So the mass changes when your object is hot, and all the measurements should be done at room temperature. I waited, I guess I didn't wait long enough for it to stay constant or become fixed number. But it is still showing the same number. So you can use the 1.305. Okay. Any questions for me? Let me see if there's any question in the chat room I did not answer. Okay. I don't see any question that pertains to me, so good. Do you have any questions about this experiment? It is a nice experiment, actually. Just the fact you see those evidences for reaction, which is color change, that's evidence for reaction. Change in texture or formation of a precipitate, that's another evidence for the reaction. Evidence for the reaction, like that means you know that something new has formed, a new compound has formed. So you're looking for evidence for reaction. When gas evolves, you're mixing like solid and a liquid, then gas evolves. When we mix the magnesium with copper sulfate solution, we saw those bubbles, and those bubbles were formation of hydrogen gas. So basically, it's showing that there is a chemical reaction taking place now. Because if there is any extra sulfuric acid, it can react with magnesium, and it gives off the bubbles and the hydrogen gas. So that's evidence for reaction. Formation of gas, formation of solid, formation of a liquid. If that is the case, which we didn't have one in these reactions, that means the actually copper nitrate and sodium hydroxide, no. Then it's the formation of the liquid. When you have copper hydroxide going to copper oxide, water is formed as one of the product. So changing color, formation of gas, formation of liquid, formation of solid. Those are evidences for chemical reaction. So you see the evidence for reaction. You see, like, you kind of prove the law for conservation of mass. And if the mass of the copper that we get is lower than the 0.4, then you have to explain why we got less than 100%. What are the possible ways that we actually lost the copper? I noticed when I was pouring out the solution, it was still blue. That means we didn't get all of the copper back. So it was just, but it was very light blue. So it means that we just lost very little mass of copper. Do you have any questions for me? Now that we are done with the experiment. Significant figures, if you are using 100, is like a times 100, then 100, that's part of the formula. And since it's part of the formula, it has unlimited number of significant figures. So you don't have to count as one significant figure. That's part of the definition. That's part of the formula for calculation. So you know you don't have to count it for it. Three significant figures, okay? Any questions for me? Okay, I'm going to stop the recording. We are not done with the lab yet, but at least I can answer your questions. But we are done with the experiment, so I can stop the recording at this point.